Okay, this part of the lecture is over volcanoes and earthquakes. And then we're also going to talk about how this impacts our rock cycle and the different minerals that we find on the earth. So basically, volcanoes, they are formed when magma reaches the earth's surface. And usually it happens through a central vent or the long crack called a fissure. And then the volcanoes form when one tectonic plate's either sliding under, such as what happens in subduction, or during a divergent plate when it's pulling away, like at the ridge. Those are volcanoes as well. So remember, magma, as soon as it hits the Earth's surface, we now call it lava. In 1980, we had the eruption of Mount St. Helens. This is the worst volcanic disaster in U.S. history. 57 people were killed and large numbers of wild animals were killed and large areas of forest were wiped out. But because of ecological succession, a lot of vegetation has returned. And there is a nice release of nutrients when we have volcanic eruption. In 1991, you have the eruption of Mount Pinatubo. It's the largest eruption of the 20th century, and it cooled the Earth's temperatures for 15 months. And despite evacuating, they evacuated 200,000 people, but several hundred people were still killed in that one. So some other benefits of volcanic activity. They create outstanding scenery in the form of majestic mountains. Some lakes, like Crater Lake in Oregon, was created in the caldera after the top blew off of the volcano. And perhaps the most important benefits is the highly fertile soils when the lava is weathered, in other words, broken down. A lot of the nutrients make it back into soil for us. This is an example of the fallout zone from Mount St. Helens. You can see how it reached all the way down to Oklahoma. This one here is Mount Pinatubo. You can see it's part of the Pacific Ring of Fire. Philippines are part of the Pacific Ring of Fire over here. Whoops. You can tell it's over here. And remember, this one decreased the global temperatures. So you can tell here, this is actually the amount of sulfur dioxide that was recorded globally, because again, there are no boundaries on our air pockets. Creation of a volcano. This one's kind of cool because it shows you how the magma upwells, and then when that happens, over time the magma will cool and form rock, and it'll cool and form rock, and then you go higher, it'll cool and form rock, so on and so on. And depending on the parent material of that particular rock, you have different types of volcanoes, and you have different intensities of volcanoes. For instance, your oceanic crust is going to form more of a basaltic volcano. It's going to be heavier, more dense. So it's not going to get as large, but it's going to get very wide. And this is typical of Hawaii. These are called shield volcanoes. Almost looks like a big old shield. It's huge. Difference between that and continental, I don't think I have a picture of these on here. No. Continental volcanoes, when those form inland, those are made more of silica, and so they're going to be much more gaseous, and they're going to get very, very tall because of the different chemical makeup that is found in those volcanoes. And so those, when they finally erupt, are much more explosive, like Mount St. Helens and Mount Pinatubo, because they had a lot more pyroclastic material on the inside to spew out, and it was just a lot more volatile. So your shield volcanoes, like the ones in Hawaii, are going to be a lot more viscous, and they aren't going to build up as high. Okay, now we have to talk about earthquakes. So earthquake, I know we've all heard of earthquakes. Basically what happens here is that there is a sudden or abrupt movement and a fault. Usually this occurs somewhere near a fault boundary. But basically what happens when you have all the plate movements, they end up, they're not smooth rocks just sliding gently, gliding by each other. They're actually all very jagged and not uniform. And so what happens as they slide, they stick or lock, and that locking mechanism builds up potential energy because they're trying to move, but they're stuck. And so as soon as you finally do get a slip, you're going to have a release of seismic energy. And that's what they call it. They call it a seismic wave, and that's that moves in all different directions, kind of like a ripple. And that's what they use to measure the magnitude of an earthquake. So the way that they measure their magnitude is by a Richter scale, and And on the Richter scale, you'll find out that a magnitude 5 earthquake is actually 10 times more ground shaking than a magnitude 4 earthquake. And the amount of ground movement from magnitude 7 would be 100 times greater than the magnitude 5. So this is your scale, and a lot of times as well, they release an aftershock. An aftershock basically decreases frequency over periods as long as several months from a major earthquake. They are sometimes preceded by foreshocks, and those happens before the main shock would actually happen. But usually the effect of earthquake, you're going to have shaking and sometimes vertical, permanent vertical or horizontal displacement of the ground. And this could have serious consequences. Most people are I guess you'd probably be the least safe inside of a building. But think about people who are in buildings, bridges, freeway overpasses, dams. Think Three Gorges dams and pipelines. So major earthquakes, a very large rock and roll geological event. Okay, the place where a earthquake begins. In other words, the place where the rock has built up that potential energy, and so when you finally release, that friction releases and the seismic wave leaves that area, that is the focus. And so I know this is silly, alliteration, whatever, but I always think of the focus and the friction as the same spot. That's where the friction and therefore potential energy buildup occurred. Okay, and then you need to know the spot on the surface of the earth. So if you are standing right above the focus on the earth, that is the epicenter. So always remember E for epicenter equals E for earth. Just a little memory trick tool there for you. Areas of the greatest earthquake risk in the United States. And so this can pretty much, you can predict, you cannot predict with accurate precision when the next earthquake is going to occur, but you can actually see on here some areas that are more active. You can make some predictions. They're not, like I said, very accurate, but if you know you had just one major slip, then it might be a little while till you have another one, that kind of thing. But so it's hard to predict them, but you definitely know where to be careful of them, and where you should be more concentrated on building safer structures. Areas of greatest earthquake risk around the world. Notice, okay, so look at this side over here, and then look at this side over here. We consider all this over here the ring of fire, and then remember we have a major collision event happening over here. So you're going to have a lot of earthquakes over here because you have India smushing into the Eurasia plate, creating the Himalaya mountains for us there. Earthquakes on the ocean floor can cause huge wave called tsunamis. Tsunami is a tidal wave caused by movement of the ocean, can travel as fast as a jet plane across the open ocean. They have ways and buoys and mechanisms put in place to try to predict tsunamis because of pressure. You can measure the changes in pressure, increase wave, altitudes of the wave. And remember, this kind of looks like from the actual seismic event, it's going to ripple out. Kind of like when you throw a rock in the water and you see the ripple in circles. That's kind of what the seismic energy acts like as well. And in deep water, the waves are very far apart, sometimes hundreds of kilometers, but their crests are not very high at all. But as the tsunami approaches the coast, it's going to slow down. Its wave crests squeeze closer together, and therefore the heights are going to grow rapidly. And then it can hit a coast as a series of towering walls of water that can level buildings. And they can be detected, like I said, through the ocean buoys, and that should provide some early warning signs. But unfortunately, what we've been doing, we've seen that a lot of coastal areas, like especially the tsunami, remember December 2004, a lot of the areas had cut down a lot of their mangrove forests, and that was acting as a natural storm protection. And Thailand, Sri Lanka, South India, Eastern Africa, no buoys or gauges were in place in the Indian Ocean to provide early warning on the tsunami in December 2004, this Indian Ocean tsunami. It was a magnitude 9.15 earthquake. And like I said, we've been cutting down mangrove forests and coral reefs, which normally reduce the energy of the tsunami. that would kind of help. So unfortunately, the extensive damage and death toll was attributed to clearing a third of the coastal forest in recent decades. In Sri Lanka, some of the damage occurred where it was illegal coral mining caused severe beach erosion. Okay, here's an example of formation of tsunami and a map of affected area of December 2004 tsunami. See what I'm down here is where I was trying to show you how the way the seismic wave works, the seismic ripple of the ocean, and you can tell here as it was fast. The waves are moving. The energy was moving fast until you near the coast. They slow down. The velocity decreases, but that impacts the amplitude. So the height increased as you move toward the inland. So the waves head inland, causing damage in their path. Over here, you had a fault. It's a thrust fault in this case. So the earthquake happened in the middle of the ocean, and that's where the energy started, right here. It's where the focus was here, and it impacted the energy. Here's an example of Indonesia before and after tsunami on June 23rd. Obviously, this is before on the left, and this is after on the right. Gravity and earthquakes can cause landslides. So mass wasting is where you have slow movement, and fast movement would be like a rock slide, avalanche, and mudslide. This is increased due to human activities like forest clearing, road building, crop growing, and building houses on steep slopes. Last March, I think it was March 29th, I recall watching that there was a cliff in Seattle. The news media, they were recording as houses literally were falling off of slopes, basically because of mass wasting. They built houses way too close to a cliff. It was gorgeous. I mean, you could see the Pacific Ocean in the background, but when your house is falling down a cliff, I guess it takes away from the beauty, the majesty of what you were seeing. So here's just some examples. Over to the right, you see avalanche, you see a landslide, and you see wasting, you see erosion. Cycling of the Earth's rocks. The three major types of rocks found in the Earth's crust are sedimentary, igneous, and metamorphic. They are recycled very slowly by the process of erosion, melting, and metamorphism. The crust is composed of rocks and minerals. Minerals are elements or inorganic compounds that occur naturally in the Earth's crust as a solid with a regular internal crystalline structure. Examples are gold, diamond, silver, salt. Ooh, whoa, woo, what happened? Salt and quartzite. Whereas rocks are a solid combination of one or more minerals found in the Earth's crust. So based on the way that the rock itself is formed, it's going to be classified as one of three different types of rocks. We have sedimentary rock that is formed through deposition, basically the cementation of other types of materials all compacted together and kind of cemented together, give you sedimentary. Then you have igneous, which is cooled lava, and then you have metamorphic, which usually has a parent rock of sedimentary or igneous that has been squished over heat and time, become metamorphic. So three major type of rocks again, continued. We have sedimentary, some examples, and you are going to have to know some examples. If you can try to at least remember one or two, that'd be awesome. We're going to do a lab with this to help you identify them, and that'll help you remember them better. But when you think of sedimentary, some clues to look for, you're going to see larger crystals kind of compacted together, or you're going to see larger bands. But this would be like sandstone, and that's very like when you have basically quartz all compacted together. If you go to the beach and you have pick up that sand in your hand, you know it's going to feel very grainy. Shale, dolomite, limestone, lignite, and bituminous coal. Igneous form the bulk of the Earth's crust because igneous is forming also majority of the oceanic crust, and there's more oceanic crust than there is continental crust. But we are very familiar with granite. We have a lot of granite in Georgia, and then lava rock. Metamorphic, it has a parent rock of something else that has been squished, and over time the heat and pressure turns it into something else. So examples are anthracite, slate, and marble. The Earth's rocks are recycled very slowly. So of all the cycles we'll talk about, we're going to talk about the nutrient cycle, biogeochemical cycle. Rock cycle is going to be the slowest of all of the processes. It takes pretty much recycles the Earth's three types of rocks. It takes millions of years for the rocks to turn from one form to another form. Here's an awesome picture. What's important to know is that you kind of can go from one rock type to another really, really quickly, or I shouldn't say quickly, but really visually. You should be able to see it really, really well. So what happens is if you are going to have an igneous or a sedimentary rock, because of heat and pressure, I'm going to use my drawing tool. Okay, so a sedimentary rock, because of heat and pressure, can become metamorphic, or igneous rock, because of heat and pressure, can become metamorphic. What's also good to know is that a metamorphic rock can be broken down. Okay, an igneous rock can be broken down. And by golly, a sedimentary rock, to be perfectly honest, can come up here and be weathered and broken down. So the process of being broken down is called weathering. The process of transporting is erosion. That's the big difference between the two. Do not confuse those two. Weathering is breaking down. Break down. And the transportation of these is erosion. Okay, so almost anything can be broken down and then eroded away, and then it can turn into back to sedimentary rock again. Well, sedimentary rock could quite possibly be melted. Sedimentary rock, because heat and pressure and stress, could be melted and turned into igneous rock. So what's important to see here is each one of these rock types can rearrange and become another rock type. That is why it is a cycle. The end.